Nah. What's up, Doc? Here we are with chapter 9. This is the review lesson. We have made it to the end of integration. Woo! So, this is just the key points from that chapter. Remember, this is not every single slide and every example. It's only the key points. If there's anything you're unsure of, you're best looking back at these individual lessons. So, let's begin. Well, remember there's an area of maths known as calculus, and calculus is divided into two key parts: differentiation and integration. Differentiation we were introduced to way back in chapter 6, and integration is just the opposite of that. So if we have our function f of x, we can differentiate it and we end up with f dash x. If we are given f dash x, we can then integrate that, to get back to f of x. When we integrate our function, we put this sign in front of it, we put this integral sign, and if our function was in terms of x, you would have dx on the end. So this would mean we are integrating our function with respect to x. However, so if you differentiate, you know how to do that. If you have 3x squared minus 4, differentiate it, you would end up with 6x. If you end up with 3x squared plus 10, you also get 6x. And if you differentiate 3x squared, you also get 6x. What's going on here? Well, with each of these, you're ending up just with 6x. If you integrate them then, how do you know if it's going to be 3x squared, or 3x squared plus 10, or 3x squared minus 4, or 3x squared plus 2.7 billion? Who knows? So what you have to do is you have to include a plus c whenever you integrate. This plus c means there may have been some constants. There may have been some number that disappeared when you differentiated. So if you integrate 6x, you'd have 3x squared and you put plus c, c for constant. In other words, there may have been some number, just like this. So to integrate, you increase the power by 1 and then you divide by the new power. Differentiating is just the opposite. You multiply by the power, then decrease the power by 1. So to integrate, you just do the opposite. So increase the power by 1, divide by the new power. So if you have x to the power of n, it becomes x to the power of n plus 1, because you're adding 1 to that power, so n plus 1. And you divide by the new power, so you then divide by n plus 1. And whenever you integrate, on the end you need plus c. You've got to have that. So for example, if you integrate x to the power of 6, add 1 to the power, so it becomes x to the power of 7, divide by the new power, so you divide by 7, and in the end you have plus c. You got it. This was another example. We're integrating this time just a number. We're integrating 3. But remember, 3 really means 3x to the power of 0, because x to the power of 0 would just end up as 1, giving us just 3. So if we add 1 to the power of x, it would be x to the power of 1, divide by 1, which would mean really we end up just with 3x plus c. But the quick way of doing it, if you ever integrate just a number, and if you're integrating with respect to x, just put an x beside the number when you integrate. And remember, plus c. It's the exact same if you have a negative index. So we're integrating m to the power of negative 5 with respect to m. So add 1 to the power. Negative 5 will increase and it will go up to negative 4. Divide by the new power, divide by negative 4, and that will be your answer. A lot of the time, if you have to then evaluate that, if you're given the value of m, well, working out a number to the power of negative 4 is sometimes confusing. So you may wish to write it with a positive index. So that would end up as, taking the negative to the side, I would move the m to the power of negative 4 down, making it m to the power of 4. So that's negative 1/4, and then, you've got 4m to the power of 4 just on the bottom. And remember, your plus c. Exact same if you have the fractional indices. You want to add 1 to the power. So if you end up with x to the power of 2 over 3, quick way of adding to the power, adding 1 to the power, is to do the top, add bottom. So if you do 2, add 3, you get 5, so it becomes 5/3. Divide by 5/3, and remember when you divide by a fraction, you can flip it upside down and then multiply by that. So dividing by 5 over 3 is the same as timesing by 3 over 5, so you can just stick that to the side, and that would be your answer with your plus c. You got it. Other examples. This one here, example 8. we had our g on the bottom of the fraction, and you cannot integrate if x, or in this case g, is on the bottom of a fraction. You also can't integrate if you have any square roots or cube roots or root signs, so you have to rewrite them. So here we had to move g from the bottom of the fraction to the top. So the 1 and the 5 would stay where they are, a fifth stays as it is, and it's just the base and the index. It's the g to the power of 3 that would move up to the top line, or just to the side. And remember, when you do move it from the bottom to the top, or vice versa, then the index would change from a positive to a negative, or vice versa. So you'd end up with this. After that, you can then integrate. Note here that you are not integrating in this step, you're only rewriting it, so do not get rid of your integral sign, do not get rid of dg, just rewrite it, and then after that, you can add 1 to the power, divide by the new power, etc. This one was the exact same, just a bit harder. Here, x was in the bottom, and we also have a root sign where we've got the 4th root of x cubed. So again, you need to rewrite that first of all. So keep your integral sign, keep dx, and just rewrite this. Put it in a form that's easy to integrate. So rewrite the root signs as negative 3 over 4, or 3 over 4, and then move up to the top, so it becomes the negative 3 over 4. From there, you can then integrate. And what do you need in the end? Plus c! We had other examples. This one again, example 11. There were quite a few of these examples. I'm going through them in depth in the lesson, so if you're unsure, just look back. But with this one here, we had x plus the square root of x squared. So again, just think about that with an index as a number. Okay, so where we've got that as x to the power of half. And then if you're squaring it, you're best to just multiply out the brackets first of all. So multiply it out, simplify it, and then integrate. Note here you are not integrating yet. We're just rewriting it, making it easy for us to integrate. This example, again, taking it a bit further, we had x to the power of 3 plus 3 divided by x squared. When you get something like that, you can do it 2 different ways. You could think about it. You've got the x cubed divided by x squared, so we can separate that. And we're also dividing the 3 by x squared, so you can write it as that. Just think about it if you were going back the way with fractions. To add the fractions, just add your numerators and keep the denominators as they are. So you're just kind of splitting it back up again into 2 fractions. And then just simplify the fractions down to this. You could also move the denominator up to the top line. And if you do that, we'll put brackets around the top. So we have x cubed plus 3 in brackets. And if you move x squared up to the top line, it becomes x to the power of negative 2. And then multiply with your brackets. If you multiply with the brackets here, again, you would end up with this. And then you can integrate. So a lot of the time you will have to rewrite your function first of all before you integrate. After that, lesson 2, we were solving differential equations, and equations like dy by dx equals 3x squared minus 7 are known as differential equations. Differential equations are equations where you have a dy by dx in them, and to solve them means to go back the way, to go back to y equals, and to do that you want to use integration. Woo! Whenever you integrate then, what do you always have in the end? Plus c! And with your plus c in the end, if you get back to y equals something plus c, it's known as the general solution. Oh yeah. But a lot of the time with these questions, you will be given more information. And if you have additional information, you can then find the value of c. If you know the value of c, you can then sub that into the general equation, or general solution rather, and that will then be known as the particular solution. So, for example, dy by dx equals 8x. It's an equation with a dy by dx, so that's a differential equation. If you integrate that, you'd end up with y equals 4x squared plus c. Because there's a plus c and it's y equals, it's known as the general solution. But if you were given more information and say c worked out to be 7, replace c with 7, and then that would then be known as your particular solution. We did a few examples with that, so find the particular solution of the differential equation dy by dx equals 8x minus 1. Given that when x is 1, y is 5, so the first thing you want to do to go back to y, you will integrate. So integrate the right hand side. Integrating 8x minus 1 will give you 4x squared minus x, and remember your plus c! So you will have that. Afterwards, again, you're given more information. So replace x with 1, y with 5. That means c is the only unknown, so you can replace c once you find it, and c works out to be 2, so we can then go back to the general solution, here I am, and replace c with 2. So you'd have y equals 4x squared minus x plus 2. That is known as your particular solution. Again, this does not include every single example. This one here, a lot of the time it won't tell you x equals and y equals. What it might tell you is that it passes through a certain point. So this example here, it tells you that the curve is passing through the point -1, 9. Just remember that obviously this is your x coordinate and this is your y coordinate. So really it's giving you the values of x and y. So after you integrate to get back to y equals, so after you find your general solution, you can then sub in x to be -1, y to be 9, and then you get the value of c. After you know the value of c, you can sub that in, and that will be your particular solution right here. Look at me! We had some more examples. Sometimes it is disguised though, so here is maybe a little trickier because it's telling you that f dash x is equal to this, and it tells you f of 4 equals 1. So find f of x. Well, you know to go back from f dash x to f of x, you've got to integrate. So you will integrate this right-hand side here. If you integrate it, you get back to x minus 2 root x, and again, you've got plus c. But it's also telling you that the f of 4 is equal to 1. So in other words, instead of f of x, we have f of 4. So we're replacing x with 4, which means then that x is going to be 4. And when you do that, then your function is going to be equal to 1. So it means that if you replace x with 4, it will all be equal to 1. So you can do that. Replace x with 4 here, so 4 minus 2 root 4 plus c, and that is equal to 1. Again, c is the only unknown, so you can say that c would equal 1. You'll just solve that. And once you know what c is, you can substitute it in to get your particular solution right here. After that, we moved on to looking at the area under a curve. Remember, differentiation, if you think way back to that, differentiation, the whole point in it is to find the gradient of a curve at a certain point. That's the main purpose of differentiation. Integration also has a main purpose, and its purpose is to find the area under a curve between the x-axis and between two x values. So you can see here, if you want the area under this curve, you've got your function y equals f of x. You're wanting that area marked with a big A between A and B, and to do that you would integrate. But when you integrate, you've also got numbers here, and these are known as your limits. So these are the values on the x-axis where the area starts and where it ends. So it's starting at A, ending at B, so we've got a lower limit and an upper limit. If you were writing down the integral associated with this shaded area, well, you would have to integrate your function. So we're integrating whatever y is equal to, so you'd integrate x plus 2, and we're integrating between 3 and 7. So these would be your limits. We did a few examples with that, just showing how you would do it and what you would write down, and then we went on to actually solving that. So this one here, it was just write down whatever integrals associated with a shaded area. So we know our function is y equals x squared, so if you want to find that area, you would integrate x square root of x rather. So if you integrate the square root of x, again you need your limits. So our lower limit is going to be 1, but we'd need the upper limit. You will always be given enough information to work that out. Here you're told that the y value is going to be 3, so you could sub that in to find x. Once we know this value of x, we can sub that in to be your upper limit. So sometimes you may have to work them out first of all. As I was just saying, A is your lower limit, B is your upper limit. You will have to integrate. When you do integrate and you have limits, you don't include a plus c. To find the area, you then integrate the function, substitute in the limits, and subtract the lower from the upper. So we did some examples with that. If you were asked to work out this area, you would be integrating your function, integrate x plus 2, integrate between 3 and 7, so you've got your lower limit and your upper limit. The smaller number always goes at the bottom, bigger number at the top. If you integrate that, you would end up with x squared over 2 plus 2x. You want to sub in the 7 and the 3, so sub the 7 in first of all, then you do minus, or take away, or subtract, and then sub in the 3, so you'd have the 3 squared over 2 plus 2 times 3. Simplify all that, and you would get down to 28. Because it's an area we want, we know we're going to have some units squared, so our squared units, so you can write that down. This example here, example 9, again this isn't every example, so you may wish to go back and look at the other ones, but for this one we weren't told what the limits would be. If you want the area enclosed between the curve and the x-axis, you're really looking for this area that's in here, and to work it out you'd have to know these 2 points first of all. So to get those 2 points, just think about what you know. Well, you know that this line y equals 4 minus x squared is going to cross the x-axis when y is equal to 0. So you can solve that to find out the two values of x. In other words, your lower and your upper limit. From there, you're just back to doing the exact same thing. Integrate and sub in the upper limit, and then minus, and then sub in the lower limit, work it all out, badoink, 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 and you get down to 10 2/3 squared units. This may be worded a slightly different way, so this time it's saying what's the value of m when you integrate and you sub in your limits, and then the answer is 4. So this one is not saying to work out what the answer is, what the area is, it's telling you the answer when you integrate that and you sub these in, you get 4. So to work out m, we'll just start it off the same way. You know you integrate between m and 1. So if you integrate this, you get x plus x squared. You know you would sub in m, then you would sub in 1, and you subtract 1 from the other. And if you do that, you get m squared plus m minus 2. But you know when you do that, what you get out is 4. So set that equal to 4, and then you can solve that. Subtract 4 from both sides, factorize your quadratic, and then you get your two values. And since m is a positive integer, then m would be equal to 2 in this case. We were then looking at the area below the x-axis. So if you work out the area here, again you would integrate your function, x squared minus 4, where we've got our limits of 2 and negative 2. If you work that out, then we get down to negative 32 over 3. What? It doesn't make sense. We don't have a negative area. Such a thing does not exist. So if you do get that, then you ignore the negative, because the area cannot be a negative. But when you work out the area below the x-axis, you end up with a negative answer. So in those cases, you ignore the negative, and you would say, so the area would just be the 32 over 3. If you work out an area above the x-axis, it's positive, and below the x-axis, it's going to be negative. So if you had something like this and you were working it out, well, if you just went for the whole thing, the lower limit is 1, the upper limit is 2, and you worked out the area, you'd end up with 0. Say, what? And that doesn't make sense. So if you have an area above and an area below, you have to work them out separately and then add them together. So here, you'd have to work out the area between 0 and 1, then work out the area between 1 and 2, and then add both answers. I do that if you look back at the individual lessons. This one here is very similar. We have an area above and an area below, so you'd work out the area between 0 and 1. You'd work out the area between 1 and 2, so you're integrating your function and subbing the values in, and then add both answers. Just remember, when you are working out this area that's below the x-axis, between 2 and 1, you end up with a negative answer. That's negative 3 1/4. But remember, you ignore the negative. So the area is just 3 1/4. Add both answers together, and you would end up with 4 1/2 for this example. Last lesson, we were looking at the area between two curves. So here you can see you've got the curve y equals f of x. Here we have the curve y equals g of x, and you want to work out the area enclosed by them between your lower limit a and your upper limit b. And to do that, what you do is you would integrate, and then you take your upper curve, so take that function, and then subtract the lower function, and then you can sub in the values of a and b after you integrate. So when you want to work out the area between two curves, it no longer matters if they're above or below the x-axis, just like it did in the last lesson. Here, all that matters is that you do top curve minus bottom curve. What you have to look out for, though, is if the lines cross. So in this case, obviously the two functions don't cross with that area that you want in this blue area. The lines aren't crossing. So all you do is you would do top curve minus bottom curve. So f of x minus g of x. Integrate that between a and b. This value of c, where you are crossing the x-axis, is no longer relevant. It's not important. All that matters is the start point and the end point. This example here, well, you can see that the lines cross. We're wanting this area that starts at A and ends at C, but the lines are crossing over at B, so you have to work out the areas separately. So to work out this area between A and B, you take the top curve, which works out to be f of x. You would subtract the bottom curve, which is g of x, so subtract them, and then sub in the limits A and B after you integrate. For this second area, again, you've got the lower limit b, you've got the upper limit c. Top curve is g of x, and you're subtracting the bottom, so it's g of x minus f of x. Integrate whatever that is, and then sub in your limits. To get the total, just add them both together. We had this example here. Sometimes we are not told again what your limits are, so we have to work them out. And to work them out, well, a lot of the time it's going to be a point of intersection. So we can see that this green area is enclosed between the parabola and our line here, and you can work out the points of intersection. If this is equal to y and this is also equal to y, you can say then that x squared is equal to 2x. Solve that and you get the 2 points that the graphs will cross, that the lines cross. So they'll cross there at 0 and also at 2, so we can find out the limits. Once you have the limits, you can then start working out the area by using integration. Top curve minus bottom curve. Here at the top we've got 2x, on the bottom you've got x squared, so it becomes 2x minus x squared. Integrate that between 0 and 2 and you will work out your value. We had another example here. Again, you're going to have to work out these points of intersection. We need to work out the lower limit. We need to work out the upper limit. So set them both equal to each other, solve that, and then you get your 3 values. 3 values because you can see that the line and the curve are crossing over here. They're crossing at 0. So again, you're going to have to split them up. So you end up with -2 and 0. Work out the area between -2 and 0 by doing top curve minus bottom curve. Do the same thing between 0 and 2, but again you need to swap it this time, so it's top curve minus bottom curve. Just be very careful when you're doing that. You will end up with 2 separate answers and then just add them together. That is it for the review of integration. Try these questions, see how you get on. It is page 140 in the Maths in Action book. It's the review of integration. Any problems, just give me a shout. Ask me in person when you see me, fire me an email, whatever you like. Have fun. Bye. Woo! Integration.
Happy birthday.